Welcome to this explainer. Okay, today we're tackling a real classic, how to optimally sort a k-sorted array. This is a highly practical computer science problem that pops up all the time in software engineering interviews, mostly because it perfectly tests your ability to optimize an algorithm by taking advantage of partially sorted data. By the end of our time together, you're going to see exactly how to approach this problem and absolutely impress any interviewer.
Here's our roadmap for today. We'll look at the k-sorted array problem, shrinking the search window, entering the min heap, Python code implementation, and finally, space and time complexity. Let's jump in.
Section 1, the k-sorted array problem. Okay, so consider the starting array, 5, 1, 9, 4, 7, 10. We're told it's a k-sorted array, and here k equals 2. But what does that actually mean? Well, it means every single number in this array is sitting, at most, 2 positions away from its final correct spot. Take the number 1, for example. It's currently at index 1, but we know it actually belongs at index 0. That's a move of just 1 spot, which is totally within our k-limit of 2.
Now, if an interviewer just hands you a completely scrambled array, you're probably going to reach for a standard sort, like merge sort or quick sort, right? And that's going to give you an O of n log n runtime. But you guys, this partial order, it's a massive clue. It's the interviewer practically whispering, hey, use this extra information. We can actually cheat the system a bit here and get a much faster runtime just by leveraging that k-limit.
Section 2. Shrinking the search window.
Think about it like this. For any specific index I in our final array, the number that belongs there isn't just floating around randomly. It absolutely has to fall within a super strict sliding window, specifically from I minus k to I plus k. So looking at index 3, the number that rightfully goes there, which is 7, has to be hiding somewhere between index 1 and index 5. We've instantly narrowed our massive search space down to just a handful of elements.
And it gets even better if we look specifically at index 0. The math simplifies beautifully. The index is 0, so the range is 0 minus k to 0 plus k. Obviously, we can't have negative indexes, right? So the absolute smallest number in the entire array has to be chilling somewhere between index 0 and index 0 plus k. With k equal to 2, that true minimum is guaranteed to be one of the first 3 elements, no question.
So here's the crucial point. Once we pinpoint that minimum value inside our tiny window, which is the number 1 here, we just swap it right into index 0. Boom! Index 0 is permanently solved. Then we just repeat that exact same logical process down the line for index 1, index 2, and so on.
But hold on a second, let's put on our optimization hats. We have a bottleneck. If we linearly scan that little window every single time we need the next smallest number, it's going to take O of k time per element. Do that for n elements, and you're looking at O of n times k. If k gets large, that's just way too slow. So ask yourself, how on earth do we dynamically track the smallest number in a sliding window without doing a slow linear scan every single time?
Section 3. Enter the min heap.
Enter the absolute hero of this problem, the min heap. It's literally perfect here because of one simple, beautiful property. It constantly keeps the minimum value sitting right at the very top of its tree, ready for us to just grab instantly. Instead of scanning, we essentially just tap the heap on the shoulder and ask, hey, what's the smallest thing you have? And it hands it right over. All right, first things first, we need to prime our min heap. We load it up with the initial k+1 values from our array. Why? Because, like we just established, the absolute minimum value for the very first spot must be somewhere in this starting group. Then the magic happens. We simply pop that absolute minimum value straight out of the heap. Right here, the heap spits out the number 1. We drop that number directly into our current insert index, index 0. Just like that, the first element is officially sorted.
But, our window needs to keep sliding forward. So, immediately after popping that one out, we take the very next available number from our unsorted array and push it right into the heap. By popping one out and pushing a new one in, our heap maintains a constant size of k+1. It perfectly mimics our sliding search window moving from left to right.
And we just keep looping this incredibly satisfying push and pop rhythm. We iterate through the rest of the array, continuously replacing our array elements with whatever minimum the heap hands us, and then feeding the heap the next upcoming value. The min heap is just dynamically handling all the heavy lifting in the background. Eventually, of course, we hit the end of our original array. We completely run out of new elements to push. When that happens, our heap still has k items sitting inside it, but we don't need to push anymore, we just empty out whatever is left. We pop them one by one, dropping them into the final empty spots of our array.
And just like that, the moment the heap is empty, our entire array is perfectly sorted. Literally, every element has naturally trickled down into its rightful place. It's brilliant.
Section 4. Python Code Implementation.
When we translate this to code, the implementation breaks down into 3 super clean phases. First, we initialize the heap by grabbing the first k+1 elements and throwing Python's heapq.heapify at them, which is incredibly efficient. Second, we dive into our main replacement loop. We start from index k+1 and go to the end, popping the minimum from the heap into our insert index and instantly pushing the new element in. And finally, phase 3, a simple while loop that just drains whatever is left in the heap once our main array is exhausted. It's clean, it's highly readable, and it literally mirrors our visual logic step for step.
Section 5. Space and time complexity.
Okay, let's break down the actual math here. Creating that initial heap takes O of k time. Then we iterate through roughly n elements. Now, because our heap never ever grows larger than k+1 elements, every single push and pop operation only costs O of log k time. Finally, draining the heap at the very end takes O of k log k. As for space complexity, well, since we strictly bound our heap to a size of k+1, the extra space we're using is a highly efficient O of k. So when we combine all those time complexity components, the O of n log k term completely dominates, which means our final, fully optimized time complexity drops from the standard O of n log n all the way down to a blazing fast O of n log k. We successfully leverage that little k variable to mathematically prove a much faster algorithm. I want to leave you with a really provocative thought to ponder. Imagine you weren't given a nice static array. What if, instead, you were handed an infinite, continuous stream of real-time data from a server, and you know that stream is k-sorted? How could you adapt this exact same min-heap strategy to sort and output that data on the fly without ever storing the whole thing in memory? Think about the power of what you just learned today. Thank you so much for joining me for this explainer, and I'll catch you next time.